For the first part of this question, we are asked to draw the displayed formula of compound J using figure 1, which shows some compounds made from a halogen alkane. So if we look at the first compound in the middle, we have CH3, CH2, CH2Br, and when this reacts with NaOH, we produce compound J. Now we know that this will react via a nucleophilic substitution reaction, but as the question is only 1 mark, we can use our knowledge of organic chemistry and knowing that we can actually just swap the Br with the OH, and this will produce CH3, CH2, CH2OH, making sure that we have drawn out all of the bonds as we asked for the displayed formula. And this will get us the mark for the first part. In this question, we are asked to name the mechanism for reaction 2 and give an essential condition used to ensure that CH3, CH2, CH2 and H2 is the major product for 2 marks. So if we look at figure 1, we can see that reaction 2 uses NH3 to convert a halogen alkane into an amine. So we know that this therefore must be via a nucleophilic substitution mechanism where the condition needed is an excess of NH3, and this is because on the nitrogen of the primary amine produced there is a lone pair that can keep reacting, and this will produce firstly a secondary amine, then when the lone pair reacts again a tertiary amine, and then finally the quaternary ammonium salt. So by using an excess of ammonia, we ensure that a primary product is produced. And this gets us both marks for this question. Moving on, we are then asked to calculate the mass in grams of CH3, CH2, CH2 and H2, produced from 25.2 grams of CH3, CH2, CH2Br in reaction 2, assuming there is a 75% yield. We are then asked to give our answer to an appropriate number of significant figures. So first of all, we need to work out the MR of our halogen alkane. So we can do this by looking at the periodic table, where carbon has an MR of 12, hydrogen has an MR of 1, and bromine has an MR of 79.9. So if you then apply this to our halogen alkane, we will have 12 plus 3 plus 12 plus 2 plus 12 plus 2 plus 79.9. And when we sum this together, we will get an MR of 122.9. We can now use our mole equation of moles equals mass over the MR, where we have the mass as 25.2 and our MR of 122.9, and this will give us a value for the moles of 0.205. And this gets us our first mark. Now the reaction actually occurs in a 1-to-1 ratio between the reactants and products, as we can see from figure 1, so we don't need to change anything in regards to molar ratios. However, we were told to assume 75% yield, so what we now need to do is multiply our 0.205 by 0.75, and this will get us a value of 0.154. And then what we now need to do, because we were asked to calculate the mass in grams of our primary amine, is do 0.154 multiplied by the MR of our amine. And again, we know that carbon has an MR of 12, hydrogen has an MR of 1, and nitrogen has an MR of 14. So therefore we can do 0.154 multiplied by, in brackets, 12 plus 3 plus 12 plus 2 plus 12 plus 2 plus 14 plus 2. And when we do this, we'll get an answer to an appropriate number of significant figures of 9.07 grams. So in this question, we get a mark for for our 0.205, a mark for our 0.154, and then a mark for our final answer of 9.07. And this gets us all 3 marks for this question. For this next question, we are told that when reaction 2 is carried out under different conditions, a compound with the molecular formula C9H21N is produced. We are then asked to draw the skeletal formula of the compound and to identify the functional group in the compound, including its classification. So for this compound, we'll have a nitrogen in the centre where we are left with C9H21. Now we know that nitrogen can only form 3 bonds, so if we split C9H21 into 3 parts, we will get 3 propyl groups which have the chemical formula C3H7. So if we now draw the skeletal formula for this, we will have a nitrogen in the centre where we will have 3 vertical lines coming off the nitrogen 3 times, and this will look like this. And as there are no single hydrogens attached to the nitrogen, we know that this must therefore be a tertiary amine. And this gets us both marks for this question. For the next part, we are told to identify the reagent and conditions used in reaction 3. So if we look at reaction 3, we can see that an alkene is produced. And as an alkene is produced from our halogen alkane, we know that this reaction must have occurred via elimination, and thus the conditions must be sodium hydroxide under ethanolic conditions. And both of these are needed for the 1 mark. For the final part of this question, we are told to name and outline a mechanism for reaction 3. So I actually mentioned this in the last part, but we know that reaction 3 is an elimination reaction as an alkene is produced from a halogen alkane. So if we draw out the displayed formula of CH3, CH2, CH2Br, we will get a carbon attached to 3 hydrogens with CH2, CH2 and Br attached. We will then have an OH minus with a lone pair, which will be attracted to the hydrogen that is opposite and adjacent to the bromine. So if we draw an arrow from the lone pair to this hydrogen, we then have an arrow going from the carbon to the hydrogen into the carbon single carbon bond to form a double bond, which leads to the carbon-bromine bond breaking, which leaves us with a carbon attached to 3 hydrogens, attached to a carbon attached to 1 hydrogen, and a double bonded carbon attached to 2 more hydrogens. And we know this is correct as we can identify this as propene, which has the structural formula C3H6, which is what is produced in reaction 3. So for the marks, we get a mark for saying that the mechanism is an elimination reaction, and we get a mark for each of our 3 arrows, which gives us 4 marks for this question. This question tells us that the rate equation for the reaction between compounds A and B is the rate equals K, which is just a constant, multiplied by the concentration of A squared, multiplied by the concentration of B. We are then told that figure 2 shows how in an experiment the concentration of A changes with time in this reaction. For the first part, we are told to draw a tangent to the curve at t equals 0. So the key with this is understanding what actually a tangent is. So a tangent in this case is a straight line to the curve that will touch the curve at 1 point, and this is when t equals 0. So if we now draw this line, we need to make sure it touches at 1 point on the curve, and we should try to use as much of the graph given to reduce the chance of an error. So when we do this, we will get a tangent that looks like this, and providing that it starts at the coordinates 0, 0.5, and goes between 5 and 12.5 along the x-axis, or time, then we do get the mark for this question. For the next part of the question, we are told to use this tangent to deduce the initial rate of reaction. And this is for 1 mark. So we know that the tangent we've drawn allows us to work out the gradient, and we know that this is what can be used to work out the initial rate of reaction. So if we then do the change in y over the change in x, we will be able to work out what the initial rate of reaction was. So if we put in values, we will get the change in y, which is 0.5, and then the change in x, which is 12. So when we do 0.5 divided by 12, we will get 0.0416, and this is in the accepted range and will get us the mark for this question. The final part for this question is worth 2 marks and tells us that the experiment was repeated at the same temperature and with the same initial concentration of B, but with a different initial concentration of A. The new initial rate was 1.7 times greater than in the original experiment, and we are asked to calculate the new initial concentration of A. So earlier in the question, we are told that the rate equals K multiplied by the concentration of A squared and multiplied by B. And if we write this out twice, we will get the rate equals K multiplied by the concentration of A squared multiplied by the concentration of B. And then also the rate equals K multiplied by the concentration of A squared multiplied by B. However, we now know that the new initial rate for reaction 2 was 1.7 times greater than the original experiment, where the initial concentration of B has stayed the same and only the concentration of A has changed. And using the graph above, we know that the initial concentration in reaction 1 was 0.5. So what we can now do is set up an equation where we have 1.7 equals K multiplied by the concentration of A squared multiplied by the concentration of B, then divided by K multiplied by the initial concentration for A, which we know using the graph above was 0.5. So this is going to be 0.5 squared multiplied by the concentration of B. So what we can do now is cancel out what we have on the top and the bottom, and this is our constant K and also our concentration of B. So what we are left with is 1.7 equals the concentration of A squared divided by 0.5 squared. So now, if we rearrange this equation to get the concentration of A squared by itself, we can do this by multiplying by 0.5 squared on both sides, and this will get us 0.425 equals the concentration of A squared, and then if we square root both sides to get rid of the squared, what we are left with is an answer to 2 significant figures of 0.65, and this gets us 2 marks for this question. In this question, we are told that a series of experiments is carried out with compounds C and D, and using the data obtained, the rate equation for the reaction between the 2 compounds is deduced to be the rate equals K multiplied by the concentration of C multiplied by the concentration of D. We are then told that in one experiment at 25 degrees Celsius, the initial rate of reaction is 3.1 times 10 to the minus 3 mole per decimeter cubed per second, when the initial concentration of C is 0.48 mole per decimeter cubed, and the initial concentration of D is 0.23 mole per decimeter cubed. We are then told to calculate a value for the rate constant at this temperature and to give its units. So if we write out what we are told in the question, we know that the rate equals K multiplied by the concentration of C multiplied by the concentration of D. We can then substitute in values that we know. So we know that the rate is equal to 3.1 times 10 to the minus 3. We don't know a value for K, but we do know that the concentration of C is 0.48 and the concentration of D is 0.23. So if we now rearrange for K by dividing by the concentration of C multiplied by the concentration of D, we will get K equals 3.1 times 10 to the minus 3 divided by 0.48 times 0.23. And this will get us a value of 2.8 times 10 to the minus 2 for the rate constant. So now, if we work out our units, we know that for our rate constant, we have the rate divided by the concentration of C multiplied by the concentration of D. So we know that the rate units are mole to the power of 1, dm to the minus 3, and s to the minus 1. And we also know that we are dividing by concentrations, which have units of mole to the 1, dm minus 3, and as there are two of them, we will write this out twice. So what we can now do is cancel anything that we have on the top and also on the bottom. So here we can cancel out a mole to the power of 1 on both the bottom and the top, and also a dm to the minus 3 on both the bottom and the top. So we are left with s to the minus 1 divided by mole to the power of 1 dm to the minus 3. But we're not done yet, as we need to use our indice laws, where when we flip an indice, a positive power will become negative and a negative power will become positive. So what we will then be left with is mole to the minus 1, dm cubed, and s to the minus 1. So if we look at where we get the marks to this question, we get a mark for rearranging in terms of K. We get a mark for our rate constant value of 2.8 times 10 to the minus 2. And then we also get a mark for correctly working out our units. And this gets us all 3 marks for this question. Moving on to the next part. This part is actually about an equation known as the Arrhenius equation, where we are told that an equation that relates the rate constant to the activation energy and temperature is given by the natural log of K equals minus activation energy divided by RT plus the natural log of A. We are then told to use this equation and our answer from part 1 to calculate a value in kilojoules per mole for the activation energy at 25 degrees Celsius, where we are told that the value for natural log of A is 16.9. The gas constant R is 8.31 joules per Kelvin per mole. And we are then told that if we were unable to complete part 1, we should use a value of 3.2 times 10 to the minus 3. But, as we were able to work out our value in part 1, we will be using 2.8 times 10 to the minus 2. So, straight away, what we should do is write out the equation. And this is the natural log of K equals minus EA divided by RT plus natural log of A. Next, we need to convert our 25 degrees Celsius into Kelvin, and we know this because our gas constant has units of joules per Kelvin per mole, so we know that the temperature is going to be measured in Kelvin as opposed to degrees Celsius. So if we now put in our values, we will have the natural log in brackets of 2.8 times 10 to the minus 2 equals minus EA which is our activation energy, divided by 8.31, multiplied by our new temperature value, which we know must be 298, because at 0 degrees Celsius, this is equivalent to 273 Kelvin. So when we add 273 to 25 degrees, we will get 298 Kelvin. And then add our value for natural log of A, which we are told is plus 16.9. So if we then subtract 16.9 from both sides, we will get minus 3.57, which was our value for the natural log of 2.8 times 10 to the minus 2, ensuring that we save this full value on our calculator and don't round. Minus 16.9 equals minus EA divided by 2476.38. So if we do minus 3.575, which is the value we've stored in our calculator, minus 16.9, we will get minus 20.475. And then if we multiply this by 2476.38, we will get our value for the minus activation energy. So we know that minus EA equals minus 50,716 joules per mole. Now, we firstly want this in kilojoules per mole, so we're going to have to divide by 1,000. And we don't want a minus activation energy, we want a positive activation energy. So if we times by minus 1, we will get 50.716 kilojoules per mole. And if we put this to two significant figures, we will get a final answer of 51 kilojoules per mole. So if we look at where the marks are allocated for this question, we get a mark for working out our value of natural log of 2.8 times 10 to the minus 2. We then get a mark for rearranging our activation energy equation. We get a mark for our minus 50,716 joules per mole. And then we get a final mark for our answer to two significant figures of 51 kilojoules per mole. And that gets us the 4 marks for this question. In this question, we are told that the aldehyde CH3, CH2, 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 CHO reacts with KCN followed by dilute acid to form a racemic mixture of the two stereoisomers of CH3, CH2, 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 CH, CN, where we are asked to give, for 1 mark, the IUPAC name of CH3, CH2, 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 CH, CN. So if we start by drawing out this compound, we have a CH3 group, followed by 3 CH2 groups, then a carbon attached to a single hydrogen, attached to an OH, also known as an alcohol functional group, and then another carbon attached to a nitrogen. So if we find the carbon skeleton, we can see that there are 6 carbons, meaning that we will have hexane in the name of this compound. Now we also have a nitrile functional group, shown by the C triple bonded to the nitrogen, but we also have an alcohol functional group. Now in this case, the nitrile takes priority and is on carbon 1. The alcohol functional group, instead of being the suffix -ol, will have the prefix hydroxy, and as it is on the second carbon, it will be 2-hydroxy. And as it is a nitrile functional group, we will put nitrile on the end after the hexane. So what we are left with is 2-hydroxy hexane nitrile. And this gets us the first mark for this question. Moving on, we are asked to describe how you would distinguish between separate samples of the two stereoisomers. So firstly, what we are going to need is a polarizing filter, as we have optically active compounds. Now this is just when we have a chiral carbon, of which is when there are 4 different groups attached to the central carbon. So here, what we'll need to do is shine plain polarized light, in which the enantiomers, which are just a pair of molecules that are mirror images of each other, will rotate the light in opposite directions. So one will rotate it anti-clockwise, and the other will rotate the light clockwise. And we get a mark for saying plain polarized light and a mark for opposite directions. We are then asked to explain why the reaction produces a racemic mixture for 3 marks. So firstly, we know that we have an aldehyde, of which will have a carbonyl functional group that can be represented by a carbon double bonded to a single oxygen. Now we know that a carbonyl group is planar, and in this case there will be a bond angle of 120 degrees. Now, as of this, the nucleophile, which in this case is the cyanide ion, can attack with equal chance from both above and below. And this is what a racemic mixture is. It is a mixture that contains equal quantities of each enantiomer of an optically active compound. So for this question, we get a mark for saying that the carbonyl group is planar, a mark for saying equal chance, and a mark for knowing that this nucleophile can attack from both above and below. For the final part, we are told that an isomer of the aldehyde reacts with KCN, followed by dilute acid to form a compound that does not show stereoisomerism. We're then asked for 2 marks to draw the structure of this compound formed and justify why it does not show stereoisomerism. So this reaction of the aldehyde and the KCN occurs via a nucleophilic addition reaction, where if we draw out what we have, I'm going to represent everything apart from the carbon attached to a hydrogen and the aldehyde functional group as an R. So what we have is R attached to a carbon, attached to a hydrogen, and then double bonded to an oxygen, where we also have the CN or cyanide ion with a lone pair. Now there is a difference in electronegativity between the carbon and the oxygen, so we'll represent this via a delta positive and a delta negative on the carbon and on the oxygen. So the lone pair will be attracted to the delta positive carbon, and this will cause one of the bonds between the carbon and the oxygen to break. So now what we have is the intermediate R attached to a carbon, attached to a cyanide, attached to a single hydrogen, and then attached to an oxygen with a lone pair and a minus charge, as here the oxygen is only forming 1 bond, where it can form a max of 2. So this lone pair on the oxygen then comes into contact with a H plus ion, which will then result in a carbon attached to a hydrogen, attached to an OH, attached to a cyanide, and then attached to an R group. So now if we draw out fully what we have CH3, CH2, 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 and then a carbon attached to a single hydrogen, attached to an alcohol functional group, and attached to a cyanide. Now, if we use our knowledge of isomerism, we can use structural isomerism, which is an isomerism where there is the same molecular formula, but a different structural formula. So here we can alter the length of the carbon chain by swapping the ethyl group with this single hydrogen. And what we will get is a carbon attached to an alcohol functional group, attached to a cyanide, attached to 2 ethyl groups, which the CH3CH2 is representative of. Now, in terms of our justification, this is why this compound does not show stereoisomerism, because there are 2 ethyl groups present, meaning that there are not 4 different groups attached. So therefore, this central carbon is not a chiral carbon. So in this question, we get a mark for our structure, and then we also get a mark for saying that there are not 4 different groups attached.
Ethanoic acid and ethane 1,2-diol react together to form the diester C6H10O4, as shown. Draw a structural formula for the diester C6H10O4. If we start by redrawing our 2 ethanoic acids and our ethane 1,2-diol, that can sometimes help to visualize what's going to happen. So if we draw one ethanoic acid group here, then we draw our ethane 1,2-diol, so we've got our 2 carbon backbone and our 2 OH groups, and then we draw another ethanoic acid group. So in this reaction, we're producing water, and in order to form water, we're going to remove the OH from the ethanoic acid and the hydrogen from the ethane 1,2-diol, and that's going to happen on both sides. That's going to help us form our ester linkages. So drawing the diester that we form, we're just removing the water, so we have our carbonyl group from the ethanoic acid, we have our oxygen from the alcohol, our 2 carbon backbone, and then the same ester group repeated at the end. So this is the diester that we form, and to get the mark for this question, you need to have this structure completely correct. A small amount of catalyst was added to a mixture of 0.470 moles of ethanoic acid and 0.205 moles of ethane 1,2-diol. The mixture was left to reach equilibrium at a constant temperature. Complete table 1, and there's space for your working below. We know from the equilibrium given on the previous page that we have a molar ratio of 2 to 1 to 1 to 2. Next, we need to work out the difference of our start and equilibrium moles. So if we did 0.470 minus 0.180, that equals 0.290 moles. So that's going to be the difference if you have the 2 molar ratio. So for water, we want a difference of 0.290 moles, and we're starting with 0, so the difference is going to be 0.290 at equilibrium. Then, because we've got the 1, we need to divide this by 2. So if we did 0.290 divided by 2, we get 0.145 moles. So we want this as our difference. So for our ethane 1,2-diol, we need to do 0.205 minus 0.145. And that's going to equal 0.06 moles, which we can then write in the table under equilibrium. Then for our diester, we want a difference of 0.145, so that means at equilibrium we're going to have 0.145 moles of our diester. And finally, just to make sure that our table is all to 3 significant figures, we can add 2 zeros to our moles of our ethane 1,2-diol. To get the 3 marks for this question, you get a mark for each of the equilibrium moles that you've calculated correctly, so 0.06, 0.145 and 0.29. You don't necessarily have to write them to 3 significant figures, it's just nice scientific practice to do so. Write an expression for the equilibrium constant Kc for the reaction. The total volume of the mixture does not need to be measured to allow a correct value for Kc to be calculated. Justify this statement. So I've just written the equilibrium in purple above so that we have it for this question. So the equilibrium constant Kc, that's the equilibrium constant in terms of concentration. So we're going to use square brackets in our expression to resemble concentration. So with an equilibrium constant, When you do its expression, you always do the forwards reaction and the products of the forwards reaction as your numerator. So for Kc, that's going to be our ester, and then we're going to multiply this by water and raise the water to the power of 2 because it has a 2 in its molar ratio. Then we're going to divide by ethanoic acid, so that's going to be square brackets CH3COOH. We're also going to square this as it's got a 2 in its molar ratio. And then we're going to multiply by ethane 1,2-diol, so HOCH2CH2OH, all in square brackets and as a large fraction. So this is the expression for Kc. Now we need to justify why we don't need to calculate the total volume for the mixture in order to calculate Kc. So there are two main reasons why you don't need to calculate volume for this mixture in order to calculate concentration for Kc. And that's because the volumes are going to cancel out in this expression. The other reason is because you have an equal number of moles or molecules on each side of the equation. So again, you don't need to calculate volume. Either of these statements will get you the second mark for this question, and your first mark comes from the correct expression for Kc. A different mixture of ethanoic acid, ethane 1,2-diol and water was prepared and left to reach equilibrium at a different temperature from the experiment in question 5.2. The amounts present in the new equilibrium mixture are shown in table 2. The value of Kc was 6.45 at this different temperature. Use this value and the data in table 2 to calculate the amount in moles of ethanoic acid present in the new equilibrium mixture. Give your answer to the appropriate number of significant figures. So the first thing to do with this question is highlight the key pieces of information. So that's our moles of our diol, our diester and water, the value of Kc that's been calculated for us at this different temperature, and that we want to work out the moles of ethanoic acid present in the new equilibrium mixture to an appropriate number of significant figures. So usually that's going to be 3 significant figures because you keep the significant figures that are in the question. In this question there are 3 significant figures for every number that we've been presented, so our answer also needs to be to 3 significant figures. So I've copied over the expression for Kc, and we're going to use this to rearrange and work out the concentration for ethanoic acid. So rearranging this expression, we're going to get that the concentration of ethanoic acid squared is equal to the concentration of our ester multiplied by the concentration of water squared divided by Kc multiplied by ethane 1,2-diol, so HOCH2CH2OH, all in square brackets. And then we can plug in the numbers for this. So if we have our concentration of ethanoic acid, again keeping it squared, then we've got the concentration of our ester, so that's going to be 0.802 divided by a volume that we don't know. Then we're going to multiply by the concentration of water squared, so that's going to be 1.15 divided by a volume squared, and then all of that divided by Kc, which is 6.45, and then multiplied by our concentration of ethane 1,2-diol, which is going to be 0.264 divided by a volume. In this expression, ethanoic acid would also be divided by a certain volume, and that means when we write ethanoic acid, we're actually just writing its moles that we don't know. So that means we can ignore volume and just directly calculate moles. So if we did the moles of CH3COOH, that's going to equal 0.802 0.802 multiplied by 1.15 squared divided by 6.45 multiplied by 0.264. And then we're going to square root all of this because we've got our moles squared in our original expression. Typing this in the calculator, you get the square root of 0.623, which equals 0.789 moles. And that is to 3 significant figures. So we can write that on our answer line because it's to the appropriate number of significant figures, and you won't get your third mark if it isn't to 3 significant figures. To get the other 2 marks for this question, you get 1 mark for your expression rearranged, so that's the moles of ethanoic acid, and then plugging in all the numbers. So this expression gets you your first mark. And then your second mark comes from ignoring volume, plugging in all your numbers, and then square rooting. So here is your second mark. And then your third and final mark is from correctly plugging these numbers into the calculator and getting 0.789 moles. Use the data booklet to help you answer this question. This question is about amino acids and peptide or amide links. Draw the structure of the zwitterion formed by phenylaniline. So a zwitterion is a neutral ion, and it's where the carboxylic acid will lose its hydrogen and the amine will gain its hydrogen. So if we look at phenylaniline, that's going to be CH, CH2, and then a benzene ring. And then we need to make our zwitterion, so COO minus and N3H plus. So this is our zwitterion, and to get the mark for this question, you must have the complete zwitterion correct. Draw the structure of serine at high pH. A high pH means basic or alkaline conditions. So this is going to deprotonate the carboxylic acid. So keeping the rest of serine correct, we're going to deprotonate our carboxylic acid and get COO minus. Because the amine is already an alkaline, or it's basic, it's not going to protonate in an alkaline or a high pH environment, just the carboxylic acid. To get the mark for this question, you must have this structure drawn correctly. Draw the structures of both dipeptides formed when phenylalanine reacts with serine. In each structure, show all the atoms and bonds in the amide link. So an amide link is a C double bond O and an NH with 2 R groups either side. So using this, we can form our amide links with phenylalanine and serine. There's going to be 2 because we can either go straight along and form the amide link where the COOH is the C double bond O, or we can flip around and have the NH2 as the NH. So this is how we're going to approach the 2 different dipeptides. So keeping the structure as we're shown in the data book first, if we draw out phenylalanine, and then we can form its peptide with serine. So here we've got the structure the same, and then we're going to have C double bond O, NH from the serine, and then CH, COOH, and CH2OH. This is our first dipeptide. Our second dipeptide, we're going to flip phenylalanine, so we're going to have HOOC, CH, CH2, and our ring, our benzene ring. And then we're going to have NH connected to a C double bond O, CH, NH2, and CH2OH. So to get the marks for this question, you get a mark for each dipeptide that is correct. So here I've drawn them both correctly. So if yours matches these, then that will give you the 2 marks, 1 for each. An amide link is also formed when an acyl chloride reacts with a primary amine. Name and outline a mechanism for the reaction between CH3, CH2, COCl and CH3, CH2, NH2. Give the IUPAC name of the organic product. Let's start with the mechanism. If we draw out our reactants first, so our acyl chloride, CH3, CH2, COCl. So this is our acyl chloride, and then we're going to draw our primary amine, which is CH3, CH2, NH2, and the nitrogen will have a lone pair. This lone pair will be attracted to the delta positive carbon, and then the lone pair will be kicked off into the oxygen. So then if we write the next stage of the mechanism, we've got CH3, CH2, C with a negative on the oxygen and our chlorine still attached. Then we have our nitrogen with its 2 hydrogens and its R group, so CH3, CH2. And nitrogen can only have 3 things attached to it, so it's going to have a positive charge. Then we're going to have another primary amine in this reaction. So if we write this in brackets, our primary amine will also have a lone pair, which will be attracted to the acidic hydrogen, and then this will be transferred into the positive nitrogen. The chlorine will be kicked off when the negative reforms its double bond with the oxygen, and this is going to produce our amide link, which will be CH3, CH2, C double bond O, NH, and then CH2, CH3. So this is our mechanism. The name of this mechanism is nucleophilic addition elimination, because we are adding a primary amine, but we're also eliminating when we're forming our side products, and in this case that would be hydrochloric acid when we're kicking off a hydrogen and a chlorine, so that's going to form hydrochloric acid or HCl. And the IUPAC name of the organic product, so the organic product is this final bit of the mechanism, and that is called N-ethyl propanamine, or amide, sorry, because that's the functional group, is the amide. The amide is this C double bond NH group in the organic product. So N-ethyl propanamide. To get the 6 marks for this question, you get 1 mark for the correct name of the mechanism. You get your 2nd mark for your primary amine attacking the carbon. You get your 3rd mark for the curly arrow from the carbon-oxygen double bond to the oxygen. You get your 4th mark for reforming the carbon-oxygen double bond. And then you get your 5th mark for your other 2 arrows in this stage. So you're kicking off the chlorine and you're forming the NH+, you're putting that bond back in, and your excess primary amine being attracted to this acidic hydrogen. That's all part of your 5th mark. Your 6th mark will come from the IUPAC name of the organic product, which is N-ethyl propanamide. There are 2 approaches to this question for the first stage. So the first stage, we want to separate this group of 4 compounds into 2 smaller groups. So if we start with K, L, M and N, the first test we could do is NaHCO3 or Na2CO3, and if we have an effervescence or the gas turns lime water cloudy, then we've got K or M. But if there's no reaction, well, that leaves us with the other 2, so that's L and N. So this is one way that we could separate into 2. Another way is we could react with silver nitrate, and this would react with the bromine. So the first one that we did, that's reacting with carboxylic acids. But silver nitrate reacts with halogens, specifically bromine, iodine and chlorine, and it will produce a cream precipitate. And that will separate into L and N, and if there's no reaction, then we're left with K and M. So next we need to distinguish between K and M and L and N. So the next one that we could do for K and M, because K has an alcohol group and M doesn't, so we can do a test for an alcohol. And the test for an alcohol would be reacting with acidified potassium chromate, so K2Cr2O7. And if this solution turns green, then that means that we have an alcohol or an aldehyde present, so that would be K. And then if there's no reaction, that's going to be M. So now we just need to separate between L and N, which we can do because N has an aldehyde functional group here. And the test for an aldehyde functional group is reacting with Tollens reagent. And the positive test is a silver mirror produced. So the silver mirror is going to show an aldehyde, which is going to be N. And then if there's no reaction, that's going to be L. So this flowchart is a great way to distinguish between all 4 compounds, and you can easily identify them. So just highlighting the functional groups that we've used the carboxylic acid in the first stage where we reacted with NaHCO3 or Na2CO3. That's testing for an acid or a carboxylic acid in this case. Then when I distinguish between K and M using acidified potassium chromate solution, then that is using the test for an alcohol or an aldehyde. But because we've already established that this can't be an aldehyde because N, which has an aldehyde, doesn't have a carboxylic acid group, then that's fine. And then L and N, using Tollens reagent, is using the aldehyde functional group here. The alternative method at the start is testing for a bromide ion, which would be here in L and N. To get the 6 marks for this question, all stages need to be covered and need to be generally correct and virtually complete. So stage 1 is that you have an initial test to separate into 2 groups. So you can have 2 groups of 2 or 1 group of 3 and 1 group of 1. In this answer, we've got 2 groups of 2, and there's 2 alternative ways we've done this. The first shown in black and the second shown in purple. Stage 2 is that you have a second test to distinguish within a group or to separate into 2 further groups. So we've distinguished within groups using either acidified potassium chromate solution or Tollens reagent. Then stage 3 is a third test which leads to a set of results / observations which distinguishes between all 4 compounds. Overall, your answer needs to be communicated coherently and show a logical progression from stages 1 to 2 and 3 to distinguish all the compounds with results for the remaining compounds stated. And that's what we've done with this flowchart. We've shown a logical method here by using a test and then two different arrows to separate for the positive test result and for the negative test result. This question is about nitrobenzenes. Nitrobenzene reacts when heated with a mixture of concentrated nitric acid and concentrated sulfuric acid to form a mixture of 3 isomeric dinitrobenzenes. Write an equation for the reaction of concentrated nitric acid with concentrated sulfuric acid to form the species that reacts with nitrobenzene. So in this question we're generating an electrophile in order to form our dinitrobenzenes. So we're reacting concentrated nitric acid and concentrated sulfuric acid. So that's the first bit of our equation. We can have HNO3 plus H2SO4. So the electrophile that we're producing is NO2 plus. And then what we're left with is H3O plus and HSO4 minus. Now we need to balance the equation by having a 2 here and a 2 here. So to get the mark for this question, you must have the full, complete equation that's written here. Name and outline a mechanism for the reaction of this species with nitrobenzene to form 1,3-dinitrobenzene. So the name of this mechanism is electrophilic because we're using the electrophile we've generated in part 1. And then it's electrophilic substitution because we're substituting a hydrogen for this NO2 plus electrophile. So if we start with our nitrobenzene, if we draw this out, we have our benzene ring with our circle and then N2O. And then we've got our electrophile N2O plus. So this delocalized ring of electrons is going to be attracted to the positive charge of our electrophile. And then we're going to form our intermediate. So most of it's staying the same. We're having our N2O and then we're going to substitute it onto position 3. So NO2 on position 3 because we've got 1, 2, 3 here. And then because it's an intermediate, we're going to have a positive charge. So it's a charged intermediate here, making sure it's centered and doesn't go past this carbon number 2 and 4. Then we're also going to have a hydrogen that's going to be delocalized back into the ring system so that it can reform and produce 1,3-dinitrobenzene. So if we draw this out, we can see how the intermediate helps us to form this, where we've got our NO2 groups here, and then we reform the ring. So this is the mechanism for this question. To get the 4 marks for this question, you get a mark for the name of the mechanism, you get a mark for your first curly arrow, you get a mark for your second curly arrow, and then you get a mark for having this curved line in your intermediate and the positive charge. So this bit gets you your 4th mark. The dinitrobenzenes shown were investigated by thin layer chromatography, or TLC. In an experiment carried out in a fume cupboard, a concentrated solution of pure 1,4-dinitrobenzene was spotted on a TLC plate coated with a solid that contains polar bonds. Hexane was used as the solvent in a beaker with a lid. The start line drawn in pencil, the final position of the spot, and the final solvent front are shown on the chromatogram in figure 3. Use the chromatogram in figure 3 to deduce the RF value of 1,4-dinitrobenzene in this experiment. Tick one box. A, 0.41, B, 0.46, C, 0.52, or D, 0.62. So RF value is calculated by the distance that the sample has travelled, and then you divide this, so you do get quite a small number, by the solvent front. So in this question, we need a ruler in order to calculate this accurately. So first we're going to work out the distance that the sample has travelled. So using a ruler, it's approximately 0.24 centimetres. And then we need the distance that the solvent front has travelled. So this is approximately 0.39 centimetres. So then if we divide this, so we do 0.24 divided by 0.39, that equals 0.62. So then the answer is D, which we can tick the box. To get the mark for this question, you must tick box D. State in general terms what determines the distance travelled by a spot in TLC. So the distance travelled by a spot in TLC is determined by the solubility of the moving phase or the mobile phase, but it's also dependent on the retention by the stationary phase. So to get the mark for this question, you must write this sentence: solubility in moving phase and retention by stationary phase. To obtain the chromatogram, the TLC plate was held by the edges and placed in the solvent in the beaker in the fume cupboard. The lid was then replaced on the beaker. Give one other practical requirement when placing the plate in the beaker. The other practical requirement that needs to be done when placing the plate in the beaker is that the solvent depth must be below the start line. And this is a sentence you must write to get the mark for this question. A second TLC experiment was carried out using 1,2-dinitrobenzene and 1,4-dinitrobenzene. An identical plate to that in question 8.3 was used under the same conditions with the same solvent. In this experiment, the RF value of 1,4-dinitrobenzene was found to be greater than that of 1,2-dinitrobenzene. Deduce the relative polarities of the 1,2-dinitrobenzene and 1,4-dinitrobenzene and explain why 1,4-dinitrobenzene has a greater RF value. In terms of the relative polarities, 1,2-dinitrobenzene is more polar than 1,4-dinitrobenzene. So 1,4-dinitrobenzene is going to be less attracted to the polar stationary phase, and this means it's going to be more attracted to the mobile phase and travel further up, creating a larger RF value. To get the 2 marks for this question, you get 1 mark for getting the relative polarities correct and 1 mark for a correct explanation. A third TLC experiment was carried out using 1,2-dinitrobenzene. An identical plate to that in question 8.3 was used under the same conditions, but the solvent used contained a mixture of hexane and ethyl ethanoate. A student stated that the RF value of 1,2-dinitrobenzene in this third experiment would be greater than that of 1,2-dinitrobenzene in the experiment in question 8.6. Is the student correct? Justify your answer. So the student is correct in this case because the solvent, which will be ethyl ethanoate mixed with hexane, that's going to be more polar. So the more polar isomer is going to be more attracted to the solvent because like dissolves like, and so this polar isomer is going to be more attracted to the solvent mobile phase and have a higher RF value as a result. To get the 2 marks for this question, you must write these 2 statements. So solvent more polar, so the polar isomer is more attracted to the solvent. This bit gets you 2 marks. Saying yes doesn't get a mark. You only get your 2 marks if you write yes with an explanation. Use the data booklet to help you answer these questions. DNA exists as 2 strands of nucleotides in the form of a double helix, with hydrogen bonding between the 2 strands. a deoxyribose molecule in a strand of DNA is shown. Name the types of groups attached to the two deoxyribose at position X and Y. So this question is a recall question, and if you don't understand it or you didn't get it right, it would be a good idea to maybe make a flashcard or a revision resource to help learn the X and Y parts of this deoxyribose molecule. So the X group is a base and the Y group is what's called a phosphate group. So to get the 2 marks for this question, you get a mark for base and a mark for phosphate group. In the DNA double helix, adenine is linked by hydrogen bonds to a molecule in the other strand of DNA. Complete the diagram below to show the other molecule and the hydrogen bonds between it and adenine. So the key words in this question is that we have adenine and we've got hydrogen bonds with another molecule. So pairs in DNA, we have A and T and G and C. So these are the 2 pairs. So as we've got adenine, we're going to pair it with thymine, which is the structure I've drawn in purple. And so this is what we're hydrogen bonding to. So if we draw out thymine, just copying it from your data booklet. So this is a relatively straightforward question, but the key is that you get the right molecule, because sometimes a common mistake is people will pair it with the wrong one, so maybe the G or the C, and that's not what the question's looking for. So that's a very common error in this question, is just making sure that you read it correctly. So here I've drawn thymine, and then we need to draw the hydrogen bonds. So we can represent these as dotted lines. So some specifications require you to label these dotted lines as hydrogen bonds or H bonds. The mark scheme for this question doesn't require you to label them, but it does need you to have the correct structure, so thymine, and you need to have it matching the data booklet. So the correct structure will get you 2 marks, but you get penalties in this question. So you get a penalty for the structure of thymine if that's not correct, the orientation of thymine if that's not correct, because you can't have hydrogen bonds on this side of thymine, or you can from this part, the NH part, but you can't with the CH3 group. So it needs to be the side where you've got your carbonyl groups, you've got your NH. That's the side you're going to have hydrogen bonds with. So not having the correct orientation can give you a penalty. Also, not drawing the hydrogen bonds can give you a penalty. So here we've shown them as dotted lines. This question is about 6 isomers of C6H10O2. Give the full IUPAC name of isomer P. The first thing we need to do is identify the longest carbon chain. So that's going to be 1, 2, 3, 4, 5 carbons. We could also go the other way, but we want to start with the highest priority group, which is our carboxylic acid group. So if we've got 5 carbons, that means we're going to have pent somewhere in the name. Then we need to look at what other groups are present. Well, we've got this carbon-carbon double bond. So that means we can have EZ isomerism, but we need to identify which it is. Is it E? Is it Z? Well, we work this out by looking at the groups attached to either side of the carbon-carbon double bond and assigning them priority. So if we look on the left-hand side, this ethyl group has the highest priority over just a hydrogen. And on the right-hand side, we have this carboxylic acid group that has the higher priority over the methyl group. So that means we have Z isomerism. Now we've numbered the carbons, so that's also going to be used in the IUPAC name. When writing an IUPAC name, you always start by identifying the type of isomerism. So that's going to be Z. Then we're going to talk about the side chains. So if we look at our 5 carbon chain, we have a methyl side group. So that's at carbon number 2, we have a methyl group. And then we're going to do pent, which is the longest carbon chain. And then we talk about the functional groups. So on carbon number 2, we have the alkene. So that's where the 2N comes from. And then we have 1-oic acid. And that's because we have the carboxylic acid group on carbon number 1. To get the mark for this question, you must have the full name correct. So Z2-methylpent-2N1-oic acid. A sample of P was mixed with an excess of oxygen and the mixture ignited. After cooling to the original temperature, the volume of gas remaining was 335 centimetres cubed. When this gas mixture was passed through aqueous sodium hydroxide, the carbon dioxide reacted and the volume of gas decreased to 155 centimetres cubed. Both gas volumes were measured at 25 degrees Celsius and 105 kilopascals. Write an equation for the combustion of P in an excess of oxygen and calculate the mass in milligrams of P used. The gas constant R is 8.31 joules per Kelvin per mole. The first thing to do with this question is highlight the key pieces of information. So that's the total volume of gas, which is 335 centimetres cubed. When you react carbon dioxide, the volume of gas that you get, which is 155 centimetres cubed. Both gases were measured at 25 degrees Celsius and 105 kilopascals. The gas constant is also a key piece of information. And then that we need to write the equation for the combustion of P in an excess of oxygen and calculate the mass in milligrams of P used. We know the formula for P from the first bit of this question, so we can start by writing the equation for combustion, which is C6H10O2, so that's P, plus oxygen, because we know we're reacting it with an excess of oxygen, and we're going to undergo combustion. There's two different types of combustion, complete and incomplete. When you have complete combustion, you form carbon dioxide. Incomplete combustion, you form carbon monoxide. In this case, we know we're forming carbon dioxide, so we're going for complete combustion. So that's CO2 and water. Now we need to balance the equation. So balancing the carbons, we need 6 carbon dioxides. Balancing the hydrogens, we need 5 waters. And then balancing the oxygens, we need 7.5 oxygens. So now we can work out the mass of P used. So we're going to use the equation PV equals nRT. So P is pressure, which is 105 kilopascals, which we then convert into pascals, which is 105,000 pascals. Then we have V, which is volume, which we'll calculate. N is the number of moles, which is what we want, so that can be X. R, we're given in the question, is 8.31 joules per Kelvin per mole. And then temperature, we need it in Kelvin, but we're given it in degrees Celsius. It's 25 degrees Celsius, which turns into 298 Kelvin. So working out volume firstly, that's going to be 335 minus 155 equals 180 centimetres cubed of carbon dioxide. And now we can rearrange this equation to work out the number of moles. So rearranging, we get that number of moles is equal to PV divided by RT. So we can plug in all the numbers here. So we've got N is equal to the pressure, so 105,000 multiplied by volume, which is 180 centimetres cubed, but we want this in metres cubed for the equation, so it's going to be 180 multiplied by 10 to the negative 6 metres cubed, so times 10 to the negative 6 here, and then we're going to divide by R, which is 8.31 and multiply by T, which is 298. So plugging this all into the calculator, we're going to get 7.632 times 10 to the negative 3 moles of carbon dioxide. Now we know from our combustion equation that we have a 1 to 6 ratio for the moles of P versus the moles of carbon dioxide. So what we can do is we can do 7.632 times 10 to the negative 3 divided by 6, which will give us the moles of P. And that's going to equal 1.272 times 10 to the negative 3 moles of P. Now we need to work out the mass of P. So firstly, that requires working out the relative formula mass, because we're going to use the equation triangle that has mass is equal to the relative formula mass multiplied by moles. So the relative formula mass of P, that's going to be 12 times 6 plus 1 times 10 plus 16 times 2, which equals 114. So then working out mass, we can just do 114 multiplied by the moles of P. So that's going to be 1.272 multiplied by 10 to the negative 3 multiplied by 114, which equals 0.145 grams. But then we want our answer in milligrams, so we need to multiply by 1,000, and that equals 145 milligrams, which we can then write on the answer line, so 145. To get the 5 marks for this question, you get a mark for the equation for combustion being correct. You get a mark for working out the volume of carbon dioxide, so 180 centimetres cubed. You get a mark for working out the moles of carbon dioxide, so 7.632 times 10 to the negative 3. That gets you your 3rd mark. Then you get a mark for working out the moles of P, so dividing by 6 and getting 1.272 times 10 to the negative 3 gets you your 4th mark. And then you get your 5th and final mark for working out the mass in milligrams, which is 145 milligrams. Isomer Q C6H10O2 is a cyclic compound. The infrared spectrum of Q is shown in figure 4, and the carbon-13 NMR spectrum of Q is shown in figure 5. Use these spectra and tables A and C in the data booklet to deduce the structure of Q. In your answer, state one piece of evidence you have used from each spectrum. So let's start by looking at what the spectra show. So if we look at figure 4, that's the IR spectra, and we have this peak here, which is between 2,500 and 3,000. So looking at table A, that's the peak for our OH acid group. So we can jot this down next to the spectra. Then I'm going to colour code table C. So we have this peak here, which is between 160 and 185, and so it's going to be this group here. And then we've also got this peak here, which is between 20 and 50, so it's showing us that we have a carbon group next to our carbonyl. So we have our purple and our green groups here. So now we can identify that we have 4 peaks on our carbon NMR, and that's going to help us to start to draw isomer Q. So it's a cyclic compound, and so that needs to be incorporated in our design. And we've got 4 peaks, which means some of the carbons are going to have the same environment. So once you've drawn a structure, always double check the number of carbon environments. So there are 2 different options for structure Q. So you can either have a 5-membered ring, and then you have your carboxylic acid group at the top, or you can have a 3-membered ring with 2 methyl groups and your carboxylic acid group at the top. So both of those will have 4 carbon environments. So if we number them, we've got 1, 2, 3, 4. And then numbering again, we've got 4, 1, 2, 3. So both of them have 4 carbon environments, so 4 peaks. They both have a carbon next to the carboxylic acid group. They both have a carboxylic acid, so it's matching all of the data that we've been given. So if we talk about the evidence from figure 4 and figure 5 now. So looking at the IR, we can talk about the OH peak, which is between 2,500 and 3,000, and it shows that we have this OH from an acid present. And then if we look at figure 5, we have 4 peaks in the NMR for figure 5, so that's our first bit of evidence. And then we have this peak at between 160 and 185, so that shows that we have a carbonyl group. And we also have a peak between 40 and 50, which corresponds to the 20 to 50 on table C. And that shows that we have this carbon next to the carbonyl group in our structure. So these are our 2 bits of evidence, one from figure 4, one from figure 5. To get the 3 marks for this question, you get 1 mark for the correct structure of Q, 1 mark for your evidence from figure 4, and then 1 mark for your evidence from figure 5. Isomers R and S are shown. Although the carbon-13 spectra of R and S both show the same number of peaks, the spectra can be used to distinguish between the isomers. Justify this statement using table C from the data booklet. Give the number of peaks for each isomer. Let's start by working out the number of peaks in R and S. So the first thing we need to do is look for any symmetry in the molecule. So both R and S have a line of symmetry in the middle here. And then we need to number the carbons. So we've got 1, 2, 3, 3, 2, 1. And the same in S. We have 1, 2, 3, 3, 2, 1. So we have 3 peaks in both R and S, which is good because they are supposed to be the same number, so we know we've counted them correctly. And so we can write 3 next to number of peaks. Now moving on to justification. There are a few different justifications to get the 3 marks for this question. The justification really focuses on looking at the carbons and how they're different in R and S. So in R, you have 4 carbons next to the carbonyl group, whereas in S, you only have 2 carbons next to the carbonyl groups. Also, in the range of 20 to 50 ppm, R will have 2 peaks and S will only have 1. So 20 to 50 is just how many carbons are next to this carbonyl group. So to get the 3 marks for this question, you get 2 marks for the justification, 1 for each sentence, and then 1 for the number of peaks. But there is an alternative justification. So with the alternative justification, that's talking about how S has this CH2-CH3 group, whereas R doesn't. And that means that S is going to have 1 peak in the range of 5 and 40 ppm, which if you look at table C, shows you that this is the alkyl type of carbon, and R doesn't have this. So that means that the lowest peak for S is much lower than R. So to get the 3 marks for this question, you get 1 mark for your first sentence, which is S has a CH2-CH3 group and R doesn't. And then you get your second mark from saying that S will therefore have a peak in the range of 5 to 40, R won't, and that means that the lowest peak for S is lower than the lowest peak for R. And then your third mark is from the number of peaks. Although the H1 spectra of R and S both show the same number of peaks, the spectra can be used to distinguish between the isomers. Justify this statement using the splitting patterns of the peaks. Give the number of peaks of each isomer. So to help with this question, I've redrawn the structures of R and S so we can identify the number of peaks in a proton spectra. So if we firstly look at where the hydrogens would be, so we're going to have 3 hydrogens here, 2 here, 2 here, and 3 here on R. And then for S, we have 2 and 3 and 2 and 3. But the carbons with a carbonyl on them don't have any more bonds for hydrogens. So in both cases, we've only got 2 peaks. We've got one that will have 2 hydrogens and one that will have 3. So we can write this here as 2. Now we need to identify why using a proton spectra is actually beneficial to distinguish between the 2 isomers. So that's looking at the splitting pattern. So if we start with R, we look at how many hydrogens are next to each environment. So looking at this environment with 3 hydrogens, well, it's next to this carbonyl with no hydrogens, so that means we're going to have a singlet. Then if we look at number 2, well, there's a line of symmetry here, so we ignore the other environment number 2, and we just look at what's next to 2 on the left-hand side. And again, it's next to this carbonyl group, so that means it's going to be a singlet. So we have 2 singlets for R, which we can write in our justification. R has both singlets. Then if we look at S, well, if we look at environment number 3 first, it's next to a hydrogen environment with 2 hydrogens. So that means we're going to have a triplet. Then if we look at environment number 2, well, it's next to an environment with 3 hydrogens and a carbonyl, so no hydrogens. So we're just going to look at the 3. So if it's next to an environment with 3 hydrogens, that means we're going to have a quartet splitting pattern. So in the justification, we can say that S will have a triplet and a quartet. And then to get the 3 marks for this question, you get 1 mark for talking about the splitting patterns in R, 1 mark for talking about the splitting patterns in S, and then 1 mark for correctly identifying that you'll have 2 peaks in the hydrogen NMR spectrum. The action of heat on 5-hydroxyhexanoic acid can lead to 2 different products. On gentle heating, 5-hydroxyhexanoic acid loses water to form a cyclic compound T, C6H10O2. Under different conditions, 5-hydroxyhexanoic acid forms a polyester. Draw the structure of T, draw the repeating unit of the polyester, and name the type of polymerization. Let's start by drawing the structure of 5-hydroxyhexanoic acid. So we need a 6-carbon backbone with a carboxylic acid group on carbon number 1 and a hydroxyl or an alcohol group on carbon number 5. So in this reaction, we're losing water, which is going to be the hydrogen from the hydroxyl group and the OH from the carboxylic acid. And we're going to lose water and make an ester. So structure T is going to have an ester functional group. So we have our ester group here, and then we have the rest of the structure, making sure that we stick to all of our carbons being the same. So we want to have 6 carbons, but we have one of them as a side group because this carbon here will be this side group. It's not going to fully make the ring. And then we need a repeating unit of the polyester. So it's the alcohol and the carboxylic acid that react together. So in the polyester, we can have the oxygen and the carbonyl, and they're going to be at the ends of our polyester. Then we have our carbon with CH3 and a hydrogen, which is just this side group that's in structure T. And then we have CH2 and then 3 of them. And that's just the 5-hydroxyhexanoic acid written as a polyester? There are two different alternative answers for this question. So you could have the ester functional group at the beginning of your polyester and then the rest of the molecule. So we have C, CH3, H, and then CH2, and then 3. So this is one alternative. You could also have your side groups at the beginning. So you have C, CH3, H, and then your main body. So that's going to be CH2, 3, C, double bond O, O, and then a line so that you can show that it's a polymer, it's going to continue. So you can either have the ester group at the beginning, the end, or at either side of your polyester. Now, because we're producing water, the type of polymerization that this is condensation. There are two types, there's condensation and addition, and this one is condensation. To get the 3 marks for this question, you get a mark for the correct structure of T, a mark for the correct repeating polyester unit, and a mark for the correct name of the polymerization, so condensation. Isomer U is shown. The polymer formed by U and the polymer formed by 5-hydroxyhexanoic acid in question 10.6 both contain ester groups that can be hydrolyzed. Draw the repeating unit of the polymer formed by U. Justify the statement that although both polymer structures contain ester groups, the polymer formed by U is not biodegradable. So whenever you have a carbon-carbon double bond, this is a sign that you have an addition polymerization happening. If you have a ester group, so a carbonyl and then a CO, that's a sign that you have condensation polymerization. So the addition polymer, if we're going to draw the repeating unit, we have CH2, C, CH3, COO, CH2, CH3, and then our line to show that it's a repeating unit. Now we need to justify. So why is U not biodegradable, but the polymer from 5-hydroxyhexanoic acid is? Well, there are two different justifications. You can look at the justification for polymer U, or you can justify 5-hydroxyhexanoic acid and why its polymer is biodegradable. So firstly, looking at polymer U. So we have non-polar carbon-carbon bonds that are really strong in the chain, and these can't be attacked by nucleophiles or acids, and that means it can't be hydrolyzed. If it can't be hydrolyzed, it can't biodegrade. Then your second justification is looking at the polymer for 5-hydroxyhexanoic acid, which has a polar ester group, and that can be attacked by nucleophiles or acids, so it can be hydrolyzed and therefore it can biodegrade. To get the 3 marks for this question, you get 1 mark for having the correct repeating unit of polymer formed by U, and then you get 2 marks for either justification being correct. This question is about 3 amines, E, F, and G. Amines E, F, and G are weak bases. Explain the difference in base strength of the 3 amines and give the order of increasing base strength. So the strength of a base depends on the availability of the lone pair on nitrogen. So this is our first marking point. Then looking at the bases individually, or the amines individually. So E, the nitrogen lone pair, delocalizes into the ring, so it's less available to donate or accept an H plus or an acid proton. Then looking at F and G, the electrons will be pushed towards the nitrogen, which is a positive inductive effect, and so it's going to be more available to donate or accept an H plus from acid. And then if we look at the order of base strength, so E will be the weakest base,
and then G, and then F is the strongest base out of the 3 amines in this question. To get the 6 marks for this question, you get a mark for lone pair on nitrogen. Nitrogen lone pair delocalizes into the ring, saying that it's less available. Then the electrons are pushed into nitrogen, so a positive inductive effect, and then more available, and then increasing base strength order is your final mark.
Amine F can be prepared in a 3-step synthesis, starting from methylbenzene. Suggest the structures of the 2 intermediate compounds. For each step, give reagents and conditions only. Equations and mechanisms are not required. So in this question, we're starting with methylbenzene and we want to make amine F, which I've copied over here from the previous question. So starting, if we draw out methylbenzene, so here we've got CH3 attached, and then it's a 3-step synthesis. In the first step, what we're going to do is we're going to turn this into a haloalkane. So we're going to have our benzene ring, and then we're going to have CH2Cl. So the reagents for step 1 are going to be chlorine and UV, and that's going to make this haloalkane. Then for step 2, we're going to do KCN, or potassium cyanide. It's got to be alcoholic and it's got to be an aqueous. So all of these conditions need to be met in this step. And what we're going to end up producing is we're going to replace this chlorine on the end with a CN, or a nitrile group. And this is step 2. This is our intermediate for step 2. And then finally, in step 3, the conditions we need are hydrogen and either a nickel catalyst or a platinum catalyst or a palladium catalyst. And what this is going to do is it's going to hydrogenate this nitrogen on the end so that we can form our amine F. So we're going to get CH2, CH2, NH2. So we're hydrogenating this carbon and this nitrogen, or the nitrile group, and we're making amine F. To get the 5 marks for this question, you get a mark for each intermediate. So that's this structure, this and this structure. Those 2 get you a mark each. And then you get your remaining 3 marks for each of the conditions for each step. So the chlorine and UV, the potassium cyanide and alcoholic and being aqueous, and then your hydrogen and your catalysts get you your 5th and final mark for this question.